Beneath the roaring winds and icy tempests of the Southern Ocean lies one of the most treacherous waterways on Earth, the Drake Passage, stretching roughly 404 miles, 650 kilometers, between Cape Horn at the southern tip of South America and the northern edge of the Antarctic Peninsula. This vast corridor of ocean serves as the only natural link between the Atlantic and Pacific. It is a place sailors both fear and revere, infamous for monstrous waves, unpredictable currents, and storms that can rise from calm seas in minutes. Named after the English privateer Sir Francis Drake, who crossed these waters in the 16th century, the passage represents both the edge of human endurance and a natural laboratory of immense geological energy. For centuries, explorers have spoken of its wrath, but what lurks beneath this remote expanse is even more formidable, a dynamic, restless sea floor where the forces shaping the planet collide in silence. On October 10, 2025, this hidden tension erupted in violent fashion. At precisely 8:29 p.m. Coordinated Universal Time, the ocean floor of the Drake Passage convulsed with the force of a 7.6 magnitude earthquake, according to the United States Geological Survey, USGS. The quake struck at a shallow depth of about 6.5 miles, 10.5 kilometers, below the surface, shallow enough to transmit its energy efficiently across the water. Its epicenter was pinpointed at 60.3 degrees south latitude and 61.9 degrees west longitude, roughly 436 miles, 702 kilometers, south-southeast of Tolhuin, Argentina, and 438 miles, 705 kilometers, southeast of Ushuaia, the southernmost city on Earth. Initial seismic readings varied, slightly depending on the monitoring station. The European Mediterranean Seismological Center registered a 7.7, while early data from other international agencies estimated up to 7.8 before revisions refined the analysis. Variations like these are routine in large-scale quakes, as sensors scattered across the planet take time to process and synchronize the complex web of seismic waves. Still, every report agreed on one fact. This was a major tectonic event, one capable of unleashing widespread effects across the southern hemisphere. The relief, if any, came from geography. The quake occurred far from densely populated regions, deep in one of the most isolated corners of the planet. Yet proximity to land was close enough to spark serious alarm. Puerto Williams, Chile, a small but vital settlement on the northern coast of Navarino Island, sits roughly 135 miles, 218 kilometers, from the epicenter, making it the nearest human community to the quake's origin. Further north, the regional hub of Punta Arenas, home to more than 117,000 residents, lies about 590 miles, 949 kilometers away. While infrastructure damage in these cities was not immediately evident, scientists feared a secondary danger that often follows such underwater quakes: tsunamis. Just 19 minutes after the quake struck, the Pacific Tsunami Warning Center, PTWC, issued an urgent advisory for the Chilean coast. Their bulletin warned that hazardous tsunami waves were possible within a 1,000-kilometer radius of the epicenter. Forecast models suggested that the first waves could strike Puerto Williams by 6:36 a.m. local time on October 10th, followed by Punta Arenas several hours later, around 2:49 p.m. The rapid issuance of these warnings underscored the speed and precision of modern monitoring systems, vital tools in preventing tragedies across coastal communities. The Hydrographic and Oceanographic Service of the Chilean Navy, SHOA, quickly echoed the alert, urging vigilance across the entire southern coastline. Within minutes, Chile's National Service for Disaster Prevention and Response, SENAPRED, activated emergency evacuation protocols for all communities within the Magallanes region, the country's southernmost territory. Residents were told to immediately move away from beaches and low-lying areas to elevated ground. Sirens wailed through coastal towns as emergency personnel fanned out to guide families to safety. Radio broadcasts and mobile alerts carried the same clear message. The ocean was unpredictable, and every second counted. President Gabriel Boric, a native of Punta Arenas himself, wasted no time in responding. He suspended his schedule and returned to La Moneda Palace in Santiago to oversee the national response. Through social media, Boric urged calm but firm action, reminding citizens that every resource of the Chilean state was mobilized. to confront the threat. "Follow evacuation instructions," he wrote. "Do not underestimate the sea." His message was amplified across television, radio, and digital networks as Chile's civil defense infrastructure shifted into full emergency mode. On the streets of Punta Arenas, local news cameras captured scenes of urgency mixed with composure. Families carried backpacks filled with essentials, blankets, food, water, documents, as they climbed toward higher ground. Vehicles streamed inland, headlights cutting through the dawn mist as people sought safety. Schools and public buildings on elevated terrain became temporary shelters. Despite the anxiety, the calm coordination reflected a population deeply familiar with living in one of the world's most seismically active nations. Chile has learned, often painfully, that readiness can mean survival. Authorities extended the warning even further south, to Chile's Antarctic research bases. Facilities such as Base Pratt and the O'Higgins Research Station, situated on the Antarctic Peninsula, were ordered to move personnel and scientific equipment to secure locations. Though hundreds of miles away, the unpredictable nature of tsunami propagation meant even these frozen outposts were not beyond potential impact. Scientists stationed there paused their experiments to monitor ocean sensors in real time, a stark reminder that even the most isolated places on Earth are linked by the restless pulse of tectonic forces. Across the border, Argentina also moved swiftly. In Tierra del Fuego, provincial authorities issued precautionary advisories, closing ports and suspending all navigation in the Beagle Channel. The Civil Protection Secretariat halted all aquatic activities and coordinated with the Chilean Navy for joint observation of sea level changes. These actions underscored a vital truth. When nature strikes, cooperation transcends politics. Both nations share not only a border, but also exposure to the same volatile geological systems that have shaped South America's southern frontier for millions of years. The Drake Passage lies at the meeting point of immense tectonic and oceanic forces, where the Scotia Plate, Antarctic Plate, and South American Plate jostle for dominance beneath some of the roughest seas on Earth. It forms part of the Pacific Ring of Fire, a 25,000-mile horseshoe of instability encircling the Pacific Basin. This zone is home to 90% of the planet's earthquakes, and about 3/4 of all active volcanoes. For Chile, earthquakes are not rare occurrences, but an inevitable fact of life, born from the slow, inexorable subduction of the Nazca Plate beneath the South American continent. This process unfolds along the vast Atacama Trench, an underwater scar plunging more than 26,000 feet, 8,000 meters, deep. Every year, the oceanic Nazca Plate creeps eastward at about 2.8 inches, 7 centimeters, forcing its edge beneath the continental crust. The friction builds colossal energy along the fault line, and when that energy releases, the Earth shakes with catastrophic power. The 7.6 event in the Drake Passage is a vivid demonstration of this ongoing planetary engine, one that never truly sleeps. In the hours following the quake, ocean buoys positioned throughout the Southern Ocean detected subtle sea level changes consistent with mild tsunami generation, though no catastrophic surges were confirmed. Chilean naval units deployed reconnaissance aircraft to monitor wave movement, while scientific vessels equipped with sonar systems began assessing the seafloor for signs of rupture or uplift. Though damage to populated areas appeared minimal, the event served as another warning of how fragile the balance between Earth's tectonic plates remains. Geologists are now studying whether this quake may be linked to broader seismic stress transfers along the Antarctic-South American boundary. Some early models suggest the tremor could slightly increase pressure along adjacent fault systems, closer to the Chilean mainland, though the risk remains speculative. Still, each event provides valuable data that helps refine understanding of this volatile region. For the global scientific community, the Drake Passage quake represents both danger and opportunity, a natural experiment in one of the least studied corners of the world. The information gathered from it may improve future tsunami prediction models and help strengthen monitoring networks across the Southern Hemisphere. Natural disasters remind us that even in the age of satellites and supercomputers, the Earth remains unpredictable. What happened beneath the Drake Passage on that October night is not just an isolated tremor. It is a reminder of the forces that shape continents, carve mountains, and command the seas. Humanity can measure and prepare, but it cannot control. If you found this report compelling and want to stay informed about the latest in geology, volcanology, and seismic events, make sure to subscribe and enable notifications so you never miss an update. Share your experiences in the comments below. Whether you've lived through an earthquake, a tsunami warning, or any natural event that changed your perspective, together awareness and knowledge can turn fear into preparation and preparation into resilience. Sicily's towering fire mountain looms over the island's east like a restless cathedral. Mount Etna in southern Italy is not only large by European standards, it is the continent's most energetic volcano, a place where the crust moves and sometimes roars. Its summit stands near 10,825 feet, about 3,300 meters, though the exact number shifts with each outburst as craters build and collapse. For centuries, Etna has cycled through eruptions and pauses, becoming both a research site and a major attraction. That appeal comes with a sober reality. Beauty and danger share the same slope. Etna's behavior does not follow one simple script. It moves along a spectrum, from modest strombolian pops and ash puffs to short, intense episodes that fling columns of molten rock skyward. In the latest chapter, fresh lava has again threaded down the flanks, cutting glowing rivers through black scoria, while orange fountains light the night. Authorities tightened access, keeping people below roughly 8,200 feet, about 2,500 meters, while instruments flagged elevated shaking. The goal is straightforward: admire the show, but keep distance while the mountain's pulse is high. A new feature has become the focal point of concern, a visible fissure on the upper slope. Drone surveys and handheld footage make the crack unmistakable. This is not a surface blemish. Fractures like this reflect underground stress as pressurized magma pries rock apart. Such openings can precede larger events, lateral eruptions lower on the cone, or, in more severe cases, structural slumps that peel away portions of the flank. Scientists have long measured a slow, persistent slide of parts of Etna seaward, a creep that usually proceeds at a walking pace each year, but hints at the forces at work inside the edifice. In rare cases elsewhere, sudden volcanic slope failures have even kicked up waves. That is not a forecast for Sicily, but it explains why a new crack instantly raises the stakes for monitoring. Even as lava fountains and glowing streams seize the eye, the volcano's internal heartbeat, the tremor signal, continues. It strengthens and dips, but together with surface deformation, it points to a system under pressure. Volcanologists are asking a simple question with complicated implications. Is this a familiar pulse in Etna's rhythm, or the start of a deeper reshaping of the mountain's plumbing and flanks? The fracture sits just below the summit crater complex, in what specialists call a subterminal zone, near the 3,000-meter contour. That belt is notorious among Etna watchers, because stress can accumulate there until the volcano chooses a side vent instead of the summit. Flank eruptions are disruptive. They can open abruptly, cross trails and roads, and send lava toward valleys long unused to flows. Their unpredictability raises risk for hikers, workers, and nearby communities alike. Ground sensors show deformation consistent with magma intrusion, hot material wedging into cracks and lifting the surface. Biomount satellites detect even when people notice nothing. The new fissure is likely the surface expression of that push. If intrusion continues, modest activity can escalate into stronger paroxysms, or if rock fails, into local collapses. Recent aerial passes mapped several small vents feeding multiple lava tongues. As they descended, the flows split and rejoined like braids in a river. The farthest fronts reached about 7,546 feet, around 2,300 meters. Higher up, the summit vents above, roughly 9,843 feet, near 3,000 meters, continued to supply fresh magma, turning the upper slopes into a moving assembly line of incandescent rock. In parallel, Italian civil protection raised the alert posture. An F1 advisory signals heightened caution and keeps the summit effectively off limits. Should conditions escalate to an F2 stance, as happened earlier this season, authorities would warn about fast-moving hot clouds and sudden hazards. A recent dip in seismic chatter may look like relief, but lulls on Etna often precede bursts. Paroxysmal episodes, sudden violent releases of pressure, can drive sky-high lava jets, loft tall ash plumes, and blast glowing clasts across wide arcs. Those class, called lapilli and volcanic bombs, can be as small as gravel or as large as a football, and they travel fast. On busy volcanoes worldwide, people have been injured by projectiles and ash clouds that outran expectations. A grim lesson from New Zealand's Wakari/White Island is that a volcano in routine activity can still switch gears without much warning. Etna is more active than most, so that lesson applies doubly here. Part of the management challenge is Etna's shape-shifting tempo. A cycle can start with tame spattering, leap into fountains, toss short-lived pyroclastic surges, then fall back to a simmer. The newly mapped fracture could mark a deviation from that familiar arc, hinting that structural stress is accumulating in a way that increases the odds of a lateral opening. Italy's National Institute of Geophysics and Volcanology reports ongoing strombolian bursts at the summit with intermittent ash visible from surrounding towns. Analysts watch more than camera images. They track the precise height of advancing lava fronts, monitor the rise and fall of harmonic tremor, and listen for infrasound signatures that reveal explosions even when weather hides the vents. Together, those metrics show magma still moving underground and feeding the surface. Because the system is unsettled, caution is wise. No one can say with confidence how the next day or two will unfold, and that uncertainty is itself a warning sign. Persistent tremor, active deformation, a fresh fissure, and multiple lava sources argue for restraint on the mountain and vigilance in the communities below. A new vent can open with little notice. An existing vent can choke and then clear with more force. Wind can swing an ash plume over a road that was clear an hour earlier. Sicilians have lived with that reality for generations. Ash on the windshield at breakfast and a faint glow on the horizon after sunset are part of the local rhythm. When instruments show rising risk, authorities close trails and restrict access. The latest fracture, together with pressure signals, argues for a stretch of heightened respect. Being prepared, knowing routes, keeping masks, having a communication plan is not alarmist. It is responsible. Round-the-clock monitoring continues. Networks of seismometers listen for swarms, too small for people to feel. GPS receivers and tilt meters register millimeter-scale motions of the ground. Thermal cameras chart the heat of flows and vents. Gas sensors measure sulfur dioxide and other emissions that rise when new magma nears the surface. Drones supply overhead views that ground teams cannot get safely. Together, these tools give a near real-time portrait of Etna's mood and help officials adjust closures and guidance. The broader scientific community follows closely because each Etna cycle teaches lessons that travel. Comparing data from Sicily with other regions sharpens models of magma ascent, flank stability, and the thresholds that tip a photogenic eruption into a hazardous one. In that sense, every measurement taken on Etna contributes to the global understanding of how our planet moves heat and material from its depths to the surface. For visitors and locals, the advice remains simple. Enjoy the spectacle from safe lookouts and respect guidance from the park and civil protection. Keep clear of summit zones. While the alert is elevated, the mountain's beauty is real, and so is its unpredictability. Respecting both is how you witness the show, without becoming part of the response. If you're passionate about geology and want more updates as this sequence evolves, stay tuned. We'll keep translating measurements and field notes into plain language. Share your thoughts below. Do you think this fissure signals a larger shift, or will Etna settle back into its familiar cadence? Your perspective helps guide what we explain next, and your caution helps keep everyone safe on the slopes. Quick glossary. Strombolian means rhythmic bursts from gas bubbles at the vent, spectacular but typically limited in range. A paroxysm is a short, powerful peak that can hurl lava high and spread ash widely. Pyroclastic flows are fast, ground-hugging clouds of hot gas, ash, and rock. Rare on Etna, but dangerous enough to drive higher alerts. Lapilli are small cinders. Volcanic bombs are larger blobs that harden in flight. Terms like these explain why rules can change quickly. Last point, volcano science is probabilistic, not prophetic. Analysts merge many weak signals, small gas shifts, subtle tremor, centimeters of tilt, into a picture of rising or falling risk, then revise it as new data arrive. Patience with restrictions and respect for the mountain make safer outcomes possible. Stay informed, stay flexible, and give Etna space. During the Second World War, the island, now officially called Ioto, known to many from that era as Iwo Jima, was a name etched into history. Today, this small volcanic outpost in the Pacific, situated roughly 1,200 kilometers, about 746 miles, south of Tokyo, is writing a different chapter. The ground has stirred yet again, and with it, a new threat has risen from below. An eruption style born not only of molten rock, but of scalding water and explosive steam that can remodel the island in a matter of minutes. At the island's southern end, Mount Suribachi, a low, brooding stratovolcano that once provided a strategic vantage point and the iconic scene of a flag raising, has become the backdrop to a fresh sequence of volcanic unrest. Kyoto is not merely a battlefield relic. It is one of the most active volcanic environments in Japan. The island perches along the Izu-Bonin-Mariana Arc, a chain of submarine and emergent volcanoes that trace the subduction of the Pacific Plate. For generations, residents and station personnel lived with the nuisances of a breathing volcano. Subtle quakes, fetid fumaroles, hot soils that steamed after rain, and sulfur in the air. Recently, however, the tempo and texture of the activity have changed, pointing to a system rebuilding pressure, reorganizing pathways, and testing the limits of the rock that contains it. Just after dawn on September 2nd, a thunderous detonation broke the morning calm and echoed across the water. What might have been dismissed as a single burst revealed itself as a complex, multi-stage event. Instead of a solitary vent, 5 separate craters opened in a short span. Each crater told its own story about where pressure was highest, where fluids could escape, and which fractures had been pried open by rising heat. The culprit was not a true magmatic fountain at the surface, but a different, notoriously unpredictable style of eruption. Phreatic blasts. In these events, hot magma at depth doesn't necessarily erupt, but it flashes shallow groundwater to steam. That water, in an instant, expands by a factor of more than 1,000, turning the subsurface into a boiler under extreme stress. If confining rocks fracture, the trapped steam tears upward, blasting out old sediments, ash, altered rock, and occasionally hot fragments ripped from magma that never quite made it to daylight. The 5 craters did not scatter randomly like buckshot. They aligned along pre-existing zones of weakness, geological seams etched into the island over many thousands of years. 3 erupted in near unison, as though triggered by the same pressure pulse, traveling up a hidden conduit network. 2 others tracked along a mapped fault, locally referenced as the Akiji/Asidi structure, revealing that much of the island's plumbing is governed by old breaks in the rock. Volcanic systems frequently exploit these weaknesses. Once a crack opens, it becomes the preferred path for fluids and heat, the way a river returns to its channel after a flood. Dimensions alone convey the violence of the blast sequence. The smallest crater measured on the order of 35 meters, about 115 feet across, while the largest yawned opened to nearly 150 meters, close to 492 feet in diameter. A span that could swallow a football field with room to spare. Carving cavities like this requires an astonishing release of energy, comparable to detonating large stores of explosives underground. And yet the most striking detail may be what some of the craters threw out. Not only shattered clay, sand, and hydrothermally altered rock, but also incandescent bits of lava. Those glowing fragments imply magma lay very shallow, perhaps only a few tens of meters beneath the surface, close enough for the blast to rip pieces from its skin. Observers reported, or in some cases inferred from deposits, brief, low-run-out pyroclastic surges, hot, turbulent clouds of ash and gas that skim along the ground at racing speeds. These were limited in extent, but their possible presence elevates the hazard profile beyond a simple steam burst, suggesting a complex interplay of heat, gas, and fragmented material. By the end of the episode, roughly 192,000 square meters, about 474,000 square feet, of terrain had been dusted and draped with new tephra. The island's map shifted yet again. Perhaps the most dramatic change was literal accretion of land. At the westernmost crater, so much debris was heaped outward that the shoreline advanced. Approximately 25,100 square meters, around 270,000 square feet of fresh surface, was added to the island's margin. On Ioto, growth is not a metaphor. It is a measurable expansion of real estate driven by eruptive power and sediment redistribution. A reminder that Earth's skin is perpetually under construction. For scientists, the craters are only the surface signature of a deeper process. A key diagnostic of that process is geodetic uplift, the island physically rising as magma and hydrothermal fluids pressurize the system below. During the first days of this sequence, precise instruments captured the ground lifting by about 10 centimeters, roughly 4 inches, per day. In the slow language of geology, that is a shout. Such rapid vertical motion implies substantial magma input or redistribution in shallow reservoirs. To make room for rising melt and superheated fluids, the brittle crust domes up like the lid of a pot under boil. Then a shift. The uplift pace slowed markedly. First, daily rise dropped by half. Then it halved again. Eventually, it settled near 0.5 centimeters, about 0.2 of an inch per day. To the casual reader, that might sound reassuring, a sign that the crisis has passed. Specialists are more cautious. A decline in uplift can mean depressurization after an eruption, but it can also indicate that fluids found new pathways, or that magma migrated laterally into a different pocket, or that gases are venting more efficiently through the newly opened fractures. In other words, the pressure did not necessarily vanish. It may have simply moved. From September 1st onward, cumulative uplift reached roughly 24 centimeters, about 9.4 inches, adding to years of steady rise. The long view is even more striking. The shoreline set during World War II now stands about 20 meters, around 66 feet, above present sea level. The beaches where soldiers once waded ashore are today perched high and dry, the ocean's old edge fossilized in terraces that step inland. This is the signature of a resurgent caldera system, a broad, subtle uplift caused by magma repeatedly refilling a large, shallow chamber and by hydrothermal fluids pressurizing overlying rock. Ioto is, in effect, the lid of a massive pressure cooker, and the cooker has been turned up for decades. Since around 2021, the island's restlessness has intensified. Minor eruptions and vigorous degassing have occurred with increasing frequency, each event a symptom of a deep engine that refuses to settle. Although the Volcanic Explosivity Index, VEI rating, assigned to the September episode is a modest one on a scale that tops out at 8, context matters. For this island in the 21st century, it is the largest event of its kind. Magnitude is not just about tall, incandescent fountains. It is also about how much the ground is rearranged, how rapidly the uplift accumulates, and how profoundly the subsurface plumbing is reconfigured. The operational consequences were immediate. Japan's self-defense forces postponed planned aircraft landing drills on Ioto and moved them to another site, an acknowledgement that even short run-out ash surges, ballistic ejections, or sudden ground deformation could endanger crews and equipment. Such decisions are never taken lightly. They reflect risk assessments that weigh the island's volatile temperament against the demands of training and logistics. Why are phreatic eruptions so unnerving? Unlike the classic lava-fed spectacle, they offer little warning. There may be subtle thermal changes, faint seismic tremor, or tiny bursts of gas composition shifts, but the trigger point can be abrupt. A blocked vent clears, a fracture tips open, groundwater flashes to steam, and an explosion follows. Depending on the geometry of the system and the permeability of the rocks, this can happen with minimal precursors that would be obvious to non-specialists. The resulting hazards include violent jets of rocks and ash, ballistics, short, fast-moving surges, and sudden collapse pits where overlying material has been evacuated. On a small island with critical infrastructure, any one of these can compel a rapid change of plans. The 5 new craters also provide scientists with a rare window into the volcano's inner pathways. Their positions and orientations illuminate the stress field, the directions in which rocks are being pulled apart or squeezed, and they reveal how pressurized fluids navigate the subsurface maze. The alignment along two principal trends points to an island-scale architecture. One set of fractures, likely tied to regional tectonics. The other controlled by the caldera's own geometry. When future episodes occur, these same alignments may reactivate, as fractured rock is easier to reopen than intact rock. Ejecta from the blasts, examined quickly in the field, included lava fragments tentatively identified as trachyte, a silica-rich composition that often forms when magma lingers in the crust, differentiating and evolving chemically. If confirmed, that would suggest a complex and potentially viscous magma system beneath the island, prone to trapping gases and developing overpressure. In such systems, the coupling between the magmatic and hydrothermal realms can be tight. Pulses of heat and volatiles from below can supercharge the steam-dominated layers above, priming them for phreatic bursts, even if the magma itself never breaches the surface. For now, the island continues to breathe. Small quakes tick by, fumaroles hiss, and the ground swells at a slower but still noteworthy pace. Whether the September sequence marks the crest of a cycle or the opening movement of a longer campaign is not yet clear. Both scenarios are plausible. Many caldera systems operate in pulses, with uplift accelerating, eruptive symptoms flaring, and then a tapering phase as the plumbing rearranges. Others ratchet forward in steps, each event creating new cracks and conduits that shorten the path from heat to water, thereby raising the odds of repeat blasts. What is unambiguous is the scale of change, already etched into the landscape. Craters dozens to hundreds of meters wide, a fresh apron of ash and debris, a measurable gain in land area, and a continuing elevation signal that leaves old coastlines stranded far inland. These are the footprints of a dynamic volcano. For those who study risk, the island presents a compact laboratory. Aviation operations, military logistics, and scientific fieldwork all must adapt to a terrain that can reconfigure itself between one survey and the next. Kyoto's story is not simply about explosions, it is about balance. As magma rises, it must find room. As steam seeks escape, it seeks the path of least resistance. When those paths are clogged, pressure builds. When they open, pressure falls, sometimes catastrophically. The 5-crater eruption sequence captured that dance in miniature. A pressurized system sought outlets along familiar faults and newly weakened rock, bled off some of its energy in violent fashion, and in the process modified the very channels that will govern whatever comes next. The practical takeaway is caution without complacency. A falling uplift rate does not mean the hazard has ended. It means the system has changed state. New fractures may now be venting gas more efficiently. Alternatively, magma may have moved laterally, charging another section of the caldera's roof. Monitoring must stay continuous and multi-pronged. High-precision GPS and tilt meters to track surface motion, seismic arrays to listen for fluid movement and fracturing, gas sensors to catch shifts in sulfur dioxide or carbon dioxide that hint at magmatic pulses, and remote sensing to map thermal anomalies or shoreline changes after each event. For an island that once symbolized a pivotal human struggle, the present saga is a reminder that the deeper contest between heat from Earth's interior and the brittle shell that covers it never ends. Kyoto has risen meters in a lifetime, carved new pits in an hour, and pushed out its shoreline in a single storm of ash and rock. Whether the next chapter brings more steam-driven violence, a lull, or a different style of eruption altogether, the island will keep telling its story in uplift lines, in crack patterns, and in the grain of fresh tephra that settles on its flanks. And for those watching, the lesson is the same as ever. The ground beneath us is not a static platform, but a living system, sometimes whispering, sometimes roaring, and always reshaping the world we think we know.